Hello, in this video we're going to look at complex equations. Well, in particular, equations that will require the use of complex numbers. So complex numbers are more than just a mathematical curiosity. In fact, these numbers are used every day by scientists, engineers, computer programmers, and mathematicians, and one of their uses is in solving equations. So let's find the roots of the equation x squared plus 4x plus 5 equal to 0 using the quadratic formula. So we'll have x equals negative b, so negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 all over 2 times 1. So x is equal to, well, negative 4 plus or minus 4 squared is going to be 16, and 16 minus 20 will be negative 4. Now, square root of negative 4, well, let's think about this. The square root of negative 4 is equal to the square root of negative 1 times 4. And we can use our roots of square roots to make it root negative 1, root 4. Well, hopefully we remember that the square root of negative 1 is equal to I. And the square root of 4 is 2. So we get 2 times I, or 2I. So this will give us negative 4 plus or minus 2i over 2. Now we can divide both of those terms by 2, so we will get negative 2 plus or minus I. So there we go. There's our solutions to the equation. X is equal to negative 2 plus I. X is equal to negative 2 subtract I. Apparently, those are the solutions to the equation. Now, maybe you don't believe that because you think, well, we're not supposed to square root negative numbers. When I get a discriminant of negative, normally, at this step, we would stop. And we would say no solution. And so it seems like maybe we cheated here by square rooting a negative. It feels like that was wrong. So what we're going to do is verify that these are solutions. So remember in math, we can verify something, we can test something. If these are solutions, then if we plug them in, they should give us 0. So let's try plugging it in. So let's take x squared. We'll do the first one here. So negative 2 plus I squared plus 4 times x, and then plus 5. Apparently this should give us 0. Now, of course, it doesn't look like 0 right now, and so maybe you're feeling a little smug. You're saying, yeah, that's right, Mr. Peters, we're not able to square root negative numbers, so of course this isn't going to work out. But let's go ahead and see. We're going to FOIL this. Negative 2 times negative 2 will be 4. Then we're going to get minus 4i plus I squared. All right, this will give us negative 8 plus 4i plus 5. All right, well, let's see what we can cancel. Negative 4i and positive 4i will go away. Remember, I squared is equal to negative 1, so we've got, do that in black, 4 minus 1 minus 8 plus 5. All right, well, 4 minus 1 is going to be 3, and then minus 8 is negative 5, and plus 5 is, we just get 0. So when we plugged it in, we got 0, which means this solution is indeed a solution. It's correct, because when you plug it in, you get 0. So x equals negative 2 plus I was indeed a solution. Now go ahead and try to verify the other one. So I encourage you to pause the video right here and try to plug in negative 2 subtract I. All right, so I'm assuming you gave it a whirl. Negative 2 subtract I squared plus 4 times negative 2 subtract I plus 5. That'll give 4 minus 4i plus I squared. Oh, sorry, that'll actually be plus 4i, because we'll get negative negative, which will be positive. Minus 8 minus 4i plus 5. So again, the 4i's cancel here. So we'll get 4 minus 1 minus 8 plus 5. which if you add that all up, again, you get 0. So this one also checks out. So both of these are the solutions. These are the complex numbers that are solutions. And it's strange for sure the first time you do it. But what this shows is that when you get a negative discriminant, you don't get a real number solution, but you do get solutions. It's just that they're complex solutions. Now, the above two solutions are actually complex conjugates of each other, right? We had -2 plus I and -2 minus I. Those are conjugates of each other because, well, you just change the sign. And this is true in general when the coefficients are real numbers. It's kind of a neat little fact. So let's find the roots of this equation using the quadratic formula, and let's see if they end up being complex conjugates. So we're going to do x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So -1 plus or minus the square root of -3. Now, we can't square root 3 nicely, but we can take the negative out. So this will be -1 plus or minus I, because the square root here of -3 is -1 times 3. So root -1 root 3, so I root 3 over 2. And then it looks a little nicer if we write it as -1 over 2 plus or minus I root 3 over 2. And so we could write that as our two solutions. X equals -1 over 2 plus I root 3 over 2. Or generally we would write the I at the end of it. So we get root 3 over 2I. And x equals -1 over 2 minus root 3 over 2I. Those are our two solutions. And if you notice, they're the same real part, but the complex, or the imaginary part, has been conjugated. So instead of being positive, then it's negative. You just switch the sign. Another remark here, now that we allow complex solutions, a second-degree polynomial, a quadratic in other words, will always have exactly two solutions. And we have this wonderful thing called the fundamental theorem of algebra. And the fundamental theorem of algebra states that every polynomial equation has exactly n solutions. So it's very cool that way. Every polynomial equation. So if you have degree 3, you're going to have 3 solutions. Degree 4, you're going to have 4 solutions. You get exactly as many solutions as you have your highest power, which is very cool. It's a nice, beautiful result. So for example, here we have a degree 3, and let's see if we can find all 3 solutions. Well, to start, we probably should see if we can do some of our synthetic. It looks like we could try the factors of 52. So x equals to factors of 52. So plus minus 1, plus minus 2, I think, yeah, 2 goes in. Plus minus 3 doesn't go in, but 4, and then so on. So I'm just going to try x equal to 4. It looks like maybe that'll work. So 1, -8, 29, -52. So we're going to try our 4 here. 1 times 4 is 4. Give you -4, -16, 13, 52, and 0. Fantastic. So I've got x minus 4, x squared minus 4x plus 13. So right away I've got one of my solutions. One of the solutions is x equal to 4. Now I need to take this and I need to figure out what this factors as, or in other words, where does this thing equal to 0? And to do that, we can now use the quadratic. So if you have a degree 3, you have to do something first, some kind of common factor or synthetic. But once you get down to degree 2, you can always use the quadratic formula. So let's go ahead and give that a whirl. So we'll get 4, x equal to 4 plus or minus the square root of -4 squared minus 4 times 1 times 13 over 2 times 1. So 4 plus or minus, well, it'll be 16 minus 52, which will be 4 plus or minus negative 36 over 2. And that's nice because 36 is a perfect square, so this will give us 4 plus or minus 6i over 2. And both of these can be divided by 2, so we're going to get 2 plus or minus 3i. So there we go. This gives us x equal to 4. That, of course, is coming from right here. And then x equal to 2 plus 3i, and x equal to 2 minus 3i. These are our three solutions. Now consider the equation x plus 5 equals to 2. This equation uses only natural numbers, but the solution is unnatural. If we were to solve this, we have to subtract 5 from both sides, and you get x equal to negative 3. Notice we had to go to the integers. It was no longer a natural number. Well, let's look at this one. We have 2x minus 3 equals 6. This equation uses the integers, but the solution is not going to be an integer. If I move that 3 to the other side, I can get 2x equals 9, and suddenly I have x equals 9 over 2, which is a fraction, not an integer. This is strange because you would expect if you used an equation with integers, maybe you can solve it with the integers. But you can create an equation using only integers that then requires the use of a non-integer solution. Well, can you think of an equation that uses only rational numbers but does not have a rational solution? Go ahead and pause the video and think about it for a second. All right, well, I'll give you a classic one. X squared minus 2 equals to 0. Because if I move that on over, I'm going to get x equals plus or minus root 2. And root 2 is irrational. So there you go. In fact, this equation didn't even have to use a rational number. I was just using integers technically, and I was able to get an irrational solution. Now, can you think of an equation that uses only real numbers but does not have a real solution? Well, this one, again, I'll use the classic. X squared plus 1 equals 0. Notice I'm only using real numbers, but when I go to solve this equation, I get x equal to plus or minus the square root of negative 1, or x is equal to plus or minus I. And hopefully this demonstrates to you that just because you're using real numbers doesn't mean you're going to get a real number as your solution. Just because you're using rationals doesn't mean you're going to get a rational number in your solution. It's very odd that you would actually get that. Quite often you use integers and rationals and you end up with irrationals or even complex numbers as your solutions. But let's just keep going. We had to go from here, and we had to go from the natural numbers, and we had to expand our number system to the integers. Then to get a solution here, we had to expand our number system to the rationals. Here we had to expand our number system to the irrationals, and then we had to expand our number system to the complex, to the imaginary numbers. And we might ask the question, do we have to keep expanding? Are we still going to have to find more and more numbers? Or is complex numbers, is there stuff after that, like super complex or hyper complex? Well, let's take a look at an equation. Let's consider x squared plus 3ix minus 4 equals 0. Notice we have a complex number, technically an imaginary number, but it's complex. We have a complex number as one of the pieces, one of the coefficients. Do you think we will require a new type of number to solve it? Do you think we're going to need something else? Maybe. Well, let's try the quadratic formula. So x equals negative 3i plus or minus the square root of 3i squared minus 4ac all over 2a. So negative 3i plus or minus 3i squared will be 9i squared plus 16 over 2. So we'll get I squared, remember, is negative 1, so negative 9 plus 16. Well, that will give us plus or minus root 7 over 2, which we could write like this. So negative 3i over 2 plus root 7, and negative 3i over 2 minus root 7. If we rearrange that with the real part first, we'd have x equal to, oh sorry, they should be over 2. If we rearrange that with the real part first, we would have root 7 over 2 minus 3i over 2, and x equal to negative root 7 over 2 minus 3i over 2. And notice, we found our solutions, and they are still complex. In fact, this is a wonderful, wonderful result. We started with an equation involving complex numbers. We solve it, and we still have only a complex number. Now, it's complex, that's definitely challenging, but we didn't need a new number. And in fact, you can show that this is true in general for complex equations, that if you have a complex polynomial, you can always solve it using complex numbers. You don't need to expand your number system to other types of numbers. Now, there are other types of number systems out there, but they're not needed for solving polynomials, and that's a very nice result. Complex numbers are the natural kind of end point for this question. You expand to the rationals and the irrationals and the reals and the complex, but you don't have to expand any further. Complex numbers are the final expansion that you need to work with polynomials. So let's try another example here. We have 2i x squared minus 4 plus 3i x plus 3 minus I equals 0. So we're going to try to solve this again using the quadratic. So let's do our best. Well, x will equal negative b, so 4 plus 3i, plus or minus the square root of b squared, so negative 4 plus 3i all squared, minus 4ac all over 2a. Alright, well we have a lot of math to do here, so let's try to do it step by step. We definitely have to do that square inside the square root. The square will square away the negative, so that doesn't matter anymore. And so maybe let's do the other part on this side here. So we have 4 plus 3i. So 4 plus 3i squared will give us 16 plus, well again, we get 12i and 12i, so 24i plus 9i squared. 16 plus 24i minus 9, so 7 plus 24i. Okay, and let's also do the other part there. We have 4 times 2i times 3 minus I. So that'll be 8i times 3 minus I. So 24i minus 8i squared. So 24i plus 8. So we'll pop both of those back in over here. So the first part is 7 plus 24i. Then we've got, well, we have to subtract. So minus 24i and then minus 8. These cancel. And this is all over 4i. Alright, so 4 plus 3i plus or minus, well 7 minus 8 is going to be negative 1. So 4 plus or minus 3i, 4 plus 3i plus or minus I over 4i. Whew, now this is definitely a challenge to write these as nice, proper, complex numbers, but we'll do both of them down here. So for the first one we have x equal to 4 plus 3i plus I over 4i, and we'll just work on simplifying that. So 4 plus 4i over 4i. Now we could divide everything by 4, so that's nice. So 1 plus I over I. Remember how to do division? We need to multiply by the conjugate. So negative I negative I. That'll give us negative I squared over negative I squared, which will give us negative I plus 1 over 1, or 1 subtract I. So there's our first value for x. Let's do the other one. So we have x equal to 4 plus 3i minus I over 4i. So 4 plus 3i, we'll make that a 2i over 4i. We divide everything by 2, so 2 plus I over 2i. Then we need to multiply by the conjugate here, so negative 2i. That'll give negative 4i minus 2i squared over negative 4i squared. So negative 4i plus 2 over 4, which we could simplify as negative 4i over 4 plus 2 over 4. So negative I plus a half. We always write the real part first. So 1/2 minus I. There's our second solution. And so again, very, very challenging because we have so many pieces here, so much complex arithmetic to do, but we still end up with solutions that are only complex. They're not any more complex than a complex number. So let's try one other example here. We're going to create an equation with solutions 1 plus I and 4 minus I. Well, just thinking back to basic algebra here, if I wanted to make an equation with solutions, let's say x equal to 2 and x equal to 3, well, I could imagine those came from factors, x minus 2 and x minus 3 equal to 0. So you just work backwards by putting x minus the factor, x minus 2 to give us the factor, and x minus 3 to give us the factor, and set it equal to 0, and well, then I guess I could just expand that. So here I would get x squared, and then minus 3x minus 2x plus 6. So x squared minus 5x plus 6 equal to 0. That would be my equation that has these as solutions. So with that in mind, let's do the same method over here for the complex. So x minus 1 plus I and x minus 4 minus I. Alright, well, let's be careful when we expand this. So first, and then outside, minus 4 minus I x minus 1 plus I x plus 1 plus I, 4 minus I equal to 0. Alright, so we just need to expand everything. So minus 4x plus ix minus x minus ix. And then over here we've got to expand this. Plus 4 minus I plus 4i minus I squared equal to 0. Well, the ix cancels, so that's nice. Nothing else I see cancels, but we can combine some terms. So this is x squared, 4x and x, that'll be subtract 5x. Now the 4 and the I, well, there's a minus I and a plus 4i, so it'll be plus 3i. And then minus I squared, that's equal to, well, I squared is negative 1, so negative negative makes positive. And finally we get x squared minus 5x plus 5 plus 3i. Now if you want, you can kind of put this last one in brackets just to show that it is a proper polynomial. We have our x squared, we have our x, then we have our constant term. The constant term has a real part and an imaginary part. Now, like I mentioned earlier, these complex numbers are fantastic because this property of complex numbers, the fact that whenever you have an equation with any kind of polynomial and complex coefficients, you still get complex solutions, this property makes the complex numbers a fantastic environment for doing mathematics. Technically speaking, the complex numbers are algebraically closed. That's the technical term, algebraic closure. So i.e., in regular words, no matter how much algebra you do, right, squaring, square rooting, multiplying, dividing, adding, subtracting with polynomials, no matter how much of that algebra you do, you will never leave the complex numbers. They are forever closed. And it's a very, very useful and very fantastic property about complex numbers, because you know that you're not going to need some kind of new number system when you're solving these equations. So make sure you take a look at these exercises, solving complex equations. The answers are at the back, and there'll be solutions on the website. As always, thanks for watching.